Anytime you have a fraction where the numerator and the denominator are both polynomials, we call that a rational function. And in fact, you already know how to integrate many rational functions. You did ones very similar to this on the review sheet that I posted under week 0 called Basically Rational. A couple of things I wanted to point out, though, when you're integrating these types of functions. Be very careful with your natural log and the absolute value signs. So in this first example here, you absolutely have to have the absolute value signs because there is the possibility that x could be less than -2, and then the natural log of 0 or anything less than 0 doesn't exist. On the other hand, if you look at this last example over here, x squared plus 4 is always positive. So in that case, you don't need the absolute value signs, but it's certainly okay to put them in there. Arctan of x, that is one that is good to just have memorized. So you don't want to have to go through and do a u sub every time you see that one, and you will see that one a lot in this class. So all of these functions here are ones that we already know how to integrate. Let's take a look at some that are a little bit more challenging. Okay, so in example 3, going back to our order of operations, we want to start with thinking, can we simplify this algebraically? That is the easiest way often to integrate something. So if you can simplify it first, start there. In this case, we cannot simplify this, but we can use long division. And anytime you have a rational function where the degree of the numerator is greater than or equal to the degree of the denominator, then that's your sign that you want to use long division. So in the numerator here, we have a degree of 4, which is greater than the denominator degree of 2. And in case you haven't done long division in a while, let's do a quick review. We have x squared plus 9. And we are dividing that into x to the 4th plus, when you do long division, good hint here, it is significantly easier if, even though we don't have an x cubed term, you want to put all of the terms in descending order. So in place of, instead of just leaving out that x cubed, we'll add in a 0x cubed plus 9x squared plus x plus 2. And long division with polynomials works exactly the same as long division with numbers. We look at the leading term of x squared and want to know how many times will x squared go into x to the 4th. And it will go into it x squared times. And now we multiply x squared by x squared plus 9. So we have x to the 4th plus 9x squared. We subtract. The 9x squared, those cancel out. The x to the 4th, they cancel out. And we bring down the x plus 2. Now in this case, we didn't end up needing the 0x cubed, but you will do one of these similar in workshop tomorrow, and you will need it then. So good habit to get into using it now. So x squared plus 9 does not go into x plus 2. If we try to divide this x squared here into x, it won't work, so this is our remainder. Okay, so we can rewrite this as the integral of x squared plus our remainder. So plus x plus 2 over x squared plus 9. And dx. Now, the x squared, we know how to simplify, but x plus 2 over x squared plus 9, let's go back to the beginning. Can we simplify this algebraically? No. Can't use long division because the degree of the numerator is less than the degree of the denominator. U sub, it looks a lot like a U sub, but because of that plus 2 in the numerator, U sub won't work. So let's try breaking the x plus 2 over x squared plus 9 into separate terms. Okay, and so we have that this is equal to the integral of x squared plus, we have x over x squared plus 9 plus 2 over x squared plus 9. Dx. And this is one form that you're going to run into quite a bit where you need to break this into two separate forms. So be on the lookout for that. You'll see it in your web work and in your homework too. And now to integrate this, integral of x squared is 1/3 x cubed plus, now if we had a 2 here in the numerator, then the numerator would be the derivative of the denominator, and so a natural log. And so since we don't have a 2, we could put a 1/2 out front, and then a 2. They cancel each other out. And that gives us the 1/2. And then 2x over x squared plus 9, that integral is the natural log of x squared plus 9. And when I write in green, a lot of times those are things that are optional, so I'll put the absolute value signs in green just so that you know you don't have to have them. You could use parentheses instead, but it's not wrong to have them. And then 2 over x squared plus 9, we want to use our Arctan formula, so we'll leave the 2 out front. And the integral of 1 over x squared plus a squared is 1 over a. So in this case, we'll have 1 over 3, arctan of x over a. And I'm a little short on room here, but we need to make sure that we add in our plus c. And we're done. So in our next example, the degree of the numerator is less than the degree of the denominator. So this is not going to be a long division. Simplifying algebraically, well, we could factor the denominator. So let's start there. So we have the integral of 2x minus 14 and in the denominator, x squared plus x minus 6, that factors to x plus 3 times x minus 2. And from here now, none of our known techniques of integration will work. But if we could somehow break it up like we did in the integral above, then maybe then we could simplify it and integrate it from there. So our goal maybe would be to break this up into two separate integrals, where in the first integral, we had that x plus 3 in the denominator. And in the second integral, we'd have the x minus 2 in the denominator. But then the question is, what should we put in the numerator to make this work? So how do we find these constants a and b so that we can break this integral up and evaluate it? Let's begin by trying to simplify it. Let's get rid of that denominator on both sides of the equation. So we'll multiply both sides through by x plus 2 times x plus 3, and then we'll distribute, and we'll use that to eliminate our denominators. So when we multiply through on the left-hand side, we have x minus 2 times x plus 3. And then when we multiply through on the right-hand side, we'll need to multiply both terms by the x minus 2 times x plus 3, and then cancel out. So on the left-hand side, the x plus 3 times x minus 2, that will cancel out with the denominator. And then on the right-hand side, the x minus 2's will cancel out. In the second term, the x plus 3's will cancel out. And so when we simplify, we're left with 2x minus 14 on the left-hand side. And that is equal to a times x plus 3 plus b times x minus 2. Okay, so now we can solve for our unknown coefficients a and b using algebra. And there's two main approaches that you'll run across. Plugging in nice values for x, and then also matching coefficients. I really like the first method, plugging in nice values for x, so I'll show you how to do that. And then matching coefficients, for the sake of time, I'll post something after lecture and go back and show you guys that method. But you can get away with doing the first method. If you're creative, you can get away with doing the first method all the time. So let's start by plugging in nice values for x. We notice that if we let x equal to 2, on the right-hand side, that second term will go away. So let's start there, and we'll label. It makes it easier to follow your work. So at x equal to 2, we sub that into both sides of the equation. And so on the left-hand side, we have 2 times 2. And in fact, I'll do this in green. It's optional because I know a lot of this you can just do the math in your head. So we have 2 times 2 minus 14. And that is equal to 5a. And then the b term goes to 0. But what I would like to see is a little bit of work. So we have 4 minus 14 is negative 10. And that's equal to 5a. And so solving for a, we have that a is negative 2. At x equal to negative 3, on the left-hand side, we have negative 20. And on the right-hand side, the first term, one with the a, goes away, and we're left with negative 5b. And subbing in, solving for b, we have that b is 4. So now we want to go back and sub that back into the original equation where we had originally an a over the x minus 2 term. So this corresponds to our negative 2. And we had a b over the x plus 3 term. So we'll put in our 4. And this we know how to integrate. We have negative 2 times the natural log of the absolute value of x minus 2 plus 4 times the natural log of the absolute value of x plus 3 plus c. So we'd like to be able to generalize this so that we can apply it to more types of rational functions. And to do this, we use a method called partial fractions. So anytime you have that rational function where you have the polynomial over a polynomial, and the denominator has a higher degree than the numerator. So remember to our earlier example, if the degree of the numerator is greater than or equal to the degree of the denominator, that's when you want to use long division. Otherwise, if you can factor the denominator into either linear or quadratic factors, then we can simplify that rational function into simpler rational functions, which then we would know how to integrate, and that technique is called partial fractions. So in the previous example that we just did, if we look at the denominator here, x minus 2, that's linear, and x plus 3, also linear, because x in both cases is raised to the first power. And when the denominator is the product of linear terms, then in the numerator you can use the coefficients a and b. But when you have either repeated linear terms or quadratic forms in the denominator, then the cases get more complicated, and there are 4 separate cases. Case 1 is the product of the distinct linear factors, like in the example we just did. Case 2, you have at least one irreducible quadratic, and no factors are repeated. So here in case 2, x squared plus 4 is a quadratic, and the x plus 3 is linear. And then case 3 and 4 are more complicated versions of case 1 and 2, where you have repeated factors. So let's do one that's slightly more complicated. Let's look at one from case 2. So we have at least one irreducible quadratic factor, and no factors are repeated. So we want to break this up where we have an x squared plus 4 in the denominator of the first term and an x plus 3 in the denominator of the second term. And notice that here I've dropped the integral signs in the dx. We're just taking a step aside and doing the algebra work, and then we'll sub it back in at the end and deal with the integration, the integrals, and the dx's. So because this first term is raised to the second power in the denominator, we have an x squared. In the numerator, we want 1 degree less. So we want something that's going to be linear in the numerator. And so we will put ax plus b. And then when the denominator is linear, then 1 degree less than that would be a constant. So in this numerator, we have plus c. Same way algebraically that we did in the previous example. We want to multiply both sides of this equation through by the x squared plus 4 times x plus 3. And so on the left-hand side, we're just left with the numerator, 3x squared minus 1. On the right-hand side, the x squared plus 4's will cancel out, and we'll be left with ax plus b times x plus 3 plus c, and now the x plus 3's cancel out, and we're left with x squared plus 4. And using the method of plugging in nice values, let's start with x equal to -3. That one kind of jumps out at us. So at x equal to -3, -3 squared is 9 times 3 is 27, minus 1 gives us 26 on the left-hand side of our equation. On the right-hand side, the first term goes to 0, and the second term simplifies to c times x squared plus 4. And in place of x squared, we have -3. -3 squared is 9 plus 4. Maybe I'll write that in just to follow the algebra here. There we go. So we have 26 is equal to 13c. And so c is equal to 2. Okay, so now we need another nice value to plug into x, but there's nothing that will make x squared plus 4 go to 0. So another nice value is x equal to 0. So let's try at x equal to 0. And subbing in x equal to 0 on the left-hand side, we're left with 3 times 0, which is 0 minus 1, or a negative 1. And that is equal to, so now we have a times 0 plus b, and that is times 0 plus 3, plus c. Now we just solved for c, so we can sub that in. We know that c is equal to 2 times 0 squared plus 4. And simplifying this, we're left with negative 1 is equal to 3b plus 8. Let's subtract 8 from both sides, so we have negative 9 is equal to 3b. And solving for b, we have that b is equal to negative 3. All right, so we need one more nice value to plug in so that we can solve for c. When we solve for c, let's try x equal to 1. So at x equal to 1, on the left-hand side, we have 3 minus 1, which is 2. And this is equal to a times 1 plus b, but we just solved for b, and we have that b is negative 3. And that's times 1 plus 3, which is 4. And for our second term now, we have c, which we know is 2 times x squared plus 4, which simplifies down to 5. And so now distributing here, we have on the right-hand side, the first term, 4a minus 12. Plus 10. We have negative 12 plus 10 is negative 2, and when we add that over to the other side, we get 4 is equal to 4a. And so a is equal to 1. All right, so we have down here, a is 1, b is negative 3, and c is 2. So we can sub that in back into our integral, and then we end up with hopefully something that we can integrate. So in the first term here, our a is 1, 1x plus b, and we said that b is negative 3. And that is plus the integral of c, here we have a 2, over x plus 3. Now, the first term here, where we have the x minus 3 in the numerator, the x squared plus 4 in the denominator, that's similar to the previous example that we just did, example 6, where we have to break that up into 2 separate terms in order to integrate it. So our first term will have a 1x in the numerator over x squared plus 4. And then for our second term, we'll have just a constant in the numerator, our minus 3. And bringing down the 2 for our third term. And so when we integrate the x over x squared plus 4, that's a natural log, we will have 1/2 natural log of x squared plus 4. The second one, that's our arctan formula again. And plugging in our missing coefficient there. And then the last one is our natural log.